let me get the recording going here. Okay, so we were at just starting section 13.5. We'd written up the Gelman matrices and the Casimirs for SU3. So I think what we're about to do is set up the, oops, got a visitor. Come on. Yeah. Yeah. Rosalind is really liking quantum field theory this summer. To set up the standard form for the for SU3. Does that jibe with everybody's notes? Come on, cat. Go on. Go on. Good cat. All right. So the first thing we do is we identify a maximal set of commuting matrices. And you'll notice that lambda 3 and lambda 8 are already diagonal. We're going to take H1 to be a half lambda, which one? Lambda 3, yeah. And that just looks like spin. All right, so in the upper corner, it looks like sigma z. Now, remember, it's not. It is and it's not. It acts the same way, but we're using the group in a different way now. This is not angular momentum, rotations and all. This is an approximate symmetry between different flavors of quark, the up, down, and strange quark. Then a second diagonal one is given by, we'll call it H2, a half lambda 8. And this one's new. The normalization here, 1/2√3. And we have 1, 1, and -2. And yeah, the normalizations for these things jump around a bit. But what we'll do is label states by the eigenvalues of H1 and H2, or actually when we get around to doing the physics, well, we're going to use a few different things. This one, wait a second here. This is isospin. Now, it's called isospin because it's not spin, but it's like spin. And it's the origin of this sort of an understanding of fundamental particles started this. Hey, Kevin. Started with the neutron and the proton. The neutron and proton are very close in mass, and the neutron actually decays into the proton. So one feels like they're very similar sorts of particle. And so people started to treat them as what was called an isospin doublet, acting on the pair of them with SU2, which is a subgroup of SU3, and is ultimately evolved into the quark model. And isospin, let's see. Yeah, there are a couple kinds of ways that SU2 comes in here. SU2 will continue to describe the weak interaction, but here we're talking about just the what's called flavor, the different types of quark. So we're just going to be mapping the quarks right here. The weak interaction we'll get to in a bit. So the other operators are like, well, they are raising and lowering operators. They're a lot like the J plus and minus, right? If you remember J plus and minus acting on a JM spin state. Anybody remember the coefficient here? You get J plus 1 minus M plus or minus 1 times J and M plus or minus 1. So J, remember, is a Casimir of the rotation group, and M gives you the Z component of the spin vector. And if you're in a representation with any given J, then M runs from minus J all the way up to plus J. In steps of 1, J takes values, integer values for bosons, half integer value for fermions. Familiar story, right? So you've worked enough with these that when we introduce 3 raising and lowering operators here, it's not going to be terrifically mysterious. I'm going to give these names that I like because they say a little more clearly what they do. Lambda 1 plus or minus I lambda 2. Then these are just the off diagonal cases. There's 1, 3 here will be a half lambda 1 plus or minus I lambda 3. And you can guess what the third one is. Plus or minus 2, 3, a half lambda 1 plus or minus lambda 2 plus or minus I lambda 3. These behave in just the same way as these J's do, except we're acting on 3-dimensional vectors comprised of an up, down, and strange quark. So these will turn one kind of quark into another. In the end, that's going to be what the gluons do. By exchanging gluons, one quark will change into a quark of a different color. We're not quite to the point in the story where we deal with color. The use of SU3 to describe the mesons and baryons together called the hadrons began with SU8 in the early 60s and evolved over that decade into a recognition that another quantum number was needed. That quantum number is called color, and it's just a way to describe a property of which you have 3. But for now, we're working with this approximate symmetry, and these guys will be raising and lowering operators. Now, there's a subtle point, because if you go show these operators to folks in the math department, did I describe this last week? I forget if we talked about this yet, but they're going to say, "Oh, you've just complexified your Lie algebra." And now, nah, you haven't. You know, we're still doing SU3 here. The thing is, all right, you know how we've chosen for quantum mechanical things or quantum field theory things, we've chosen often Hermitian generators. We want to write the Hamiltonian and like angular momentum, things like this, as Hermitian operators. All right, so the time translation operator is what? Well, it's generated by an anti-Hermitian transformation, right? The Lorentz transformations, they're all anti-Hermitian. But we don't write them that way. What we do is we choose like the Pauli matrices for rotations there. Yeah, suppose we're just talking about rotations. Still, we choose the Pauli matrices. That's not a proper choice for a Lie algebra in the formal sense, because there's an I here, sigma k, right? That's the commutation relation for the Pauli matrices. These are not generators, strictly speaking, of the rotation group, but are, I times sigma. In fact, minus I over 2 times the Pauli matrices. I like to call those tau. And those satisfy tau I, tau j equals epsilon ijk. You get rid of the 2, you get rid of the I, whoops, and then tau here. So we can choose some generators where the structure constants are real. And then in order to find the group, you exponentiate linear combinations, real linear combinations of those generators. Boom, everybody's happy. we're talking about SO3 here, or well, no, in this case, sorry, SU2. But we like to use Hermitian generators. So what do you do? Well, no big deal. You just write this as e to the I, actually I phi over 2 n dot sigma. You put an explicit I in when you exponentiate to find the group. If you want to strictly stick to the Lie algebra, then the Lie algebra is vectors like, well, what do you need? I, some vector dot, let's call this an element of the Lie algebra, and stick the I in. This is not a problem. Okay, if you insist on taking purely imaginary linear combinations of the Pauli matrices, that is the Lie algebra of SU2, not the complexified SL2C. So by restricting the coefficients of your Hermitian generators, it's perfectly easy to keep the same Lie algebra. For these guys, what you do is something like this. You put in an explicit I, and you've got your lambdas, and the combination you take is what you need. What you need is whatever you multiply E by. Let me see how I do this. Yeah, E plus. So if I take some complex number with the raising operators, I need to take the complex conjugate with the lowering operators, where n is replacing that pair. And then we need an overall I and a sum on m here. And then for the diagonal ones, you need to put in the I with have I got it here? Yeah. So just AI, HI, sum 1 to 2 times the I here. And we've got 2 real parameters, 3, wait a minute, sorry, 6 real parameters, 7, 8. 8 real parameters to describe the Lie algebra. So you have an answer when your friends over in math say, oh, you've just complexified the algebra. You tell them, no, we take this linear combination and we're still talking about SU3. So yeah, I've been challenged that way. I didn't know what to answer at the time, so I figured it out, right? So I'm saving you the problem of dealing with that question. Okay, so in any case, by adding a rule saying, okay, when we form the vectors of the Lie algebra, we take this kind of linear combination of those generators. Cool, you know, that is the Lie algebra SU3, 8-dimensional vector space. And then let's see, I gave you a little exercise with SU2 there. So now we want to find the root vectors. This stuff gets fairly abstract, and you know, I sort of have to relearn it every time I talk about it. But there's a lovely little book by Lichtenberg. It's like group theory for physics or something. You know, slim little thing. The first field theory class I ever had was from Wally Greenberg at U of Maryland, and he said, you know, go read that book, and so I did. You know, it took about a week. You know, it's an easy little book to go through, but it does all this kind of stuff. You know, it lays out how you handle groups, and it's, you know, really nice to, you know, I think it's got Young tableau in there and all the sort of stuff we're doing now, these standard representations, all in one place, thought through and easy to read. So now what we do is we want to identify combinations. Actually, these are the combinations that give the standard form. If you look, you'll find that these satisfy, if I take either of these diagonal matrices and I take the commutator with any of these raising and lowering operators, we always will get a multiple of the same thing. So you'll get some constant here that depends on ion alpha, and you'll get the same E alpha plus or minus back. So I claim this is the standard form for SU3. And the, Guillermo.
All right, so I'm getting a little lost in the math, in the construction of
Sure.
all these operators and vectors.
Yeah.
I guess like just a question for the near future, like what are we trying to get at? Like, are we trying to get like a standard representation? Is that what the whole point of
this is the standard form of the Lie algebra SU3.
Okay. Okay. Thank you.
So yeah, I'm more or less giving you the answer here rather than deriving it. I think we went through standard form last week. Am I remembering correctly? What you do is basically commutators of this form are an eigenvalue problem. If you use, say, the adjoint representation for the algebra and write out, what this looks like in terms of some matrices, you'll find that I think I did this. I expanded H and expanded E in some basis and showed that in order to solve for the coefficients of E, given whatever combination H is, you were essentially solving an eigenvalue equation. We know how to solve eigenvalue equations. I have you do it for SU2, and you're just going to find sigma 1 plus or minus I sigma 2 as the solution. It's the only solution. And I want you to show that. So you'll get a little practice with this. But for SUN, this is not hard. It always takes this form. It's not hard to show. We have explicit forms for these lambdas, right? We wrote them down last week. There's these 3x3 things that look like generalized Pauli matrices. And if you look at what these combinations are, each of these is a matrix like, all right, E plus, the plus case, you have 0, 1, 0, 0, 0, 0, 0, 0, 0. Every one of these, the minus one has the one over here. Okay, so if you write these out in terms of the lambdas we wrote last week, you'll see that, there's a 1 off diagonal somewhere for each of these 6. And that means that if this acts on, say, a D quark, if this is UDS, let's write a general one here, right? What it's going to give is it's going to put the D up top, and so basically it changes from the D position to the U position. It's converting a D quark to a U quark. So that's what these guys are doing. They're moving you around among that triple of quarks.
Follow up.
Is that okay? Does that help? Have I answered your question?
Yes. I just have a follow up.
Good. Yeah. What you got?
So here in the book, you said that this is what you do. You set the Lie algebra and you find the standard form of it. I guess the question would be like, why is it so important that we put it in a standard form?
Okay. We're going to do this graphically. This is going to tell us how to step through the irreducible states of SU3. Where we'll use that is in the description of the mesons and baryons. So what we're going to find, let's just talk a little bit about where we're headed here. So let's see, if we draw things in the basically the H1, H2 plane. Then, all right, yeah, why not, right? Eigenvalues of H1 and H2, right? So we define HI on some lambda I to be, well, let's not use lambda, alpha I, to give us eigenvalues. And there are two of those, right? So we plot those here, alpha 1, alpha 2. Right? So we want to be able to plot the possible states. Now, go back to angular momentum, right? What do? Have you, okay, I know, Guillermo, you've seen Clebsch-Gordon series, right? Where you multiply angular momenta to get other angular momentum states. Have you seen it? How about you, Kevin, Eli? Is that familiar to you? Let me review that, because that's really what we're doing here. Let me back up. This stuff, I know it's really abstract. I remember the first time I saw this. What? But we're headed for the eightfold way here, which was a really cool thing, that happened in the 60s. The initial understanding of the relationship between the baryons and the mesons as they derive from quarks. So, it's understanding this that Murray Gell-Mann in 1962 realized that using this stuff to describe baryons and mesons really made sense of a whole lot of particles they were seeing. So, that's what we're doing. We're doing background work for particle physics here. Okay, so let's remember how the whole Clebsch-Gordon thing works. Let's see. If we want to right, we have two diagonal operators, J squared and JZ, right? And we label our states by eigenvalues of those, the two diagonal operators. So we're going to write two eigenvalues in our states. And this is going to be J plus 1, H bar squared, Jm. Because J is a Casimir, none of these operators are going to change J. And then JZ acting on Jm gives M H bar, Jm, right? So we've chosen these states to be labeled by eigenvalues of the diagonal operators, a maximal set of diagonal operators. Go back and read section 2 of the book, right? I went through this for SU2 in detail. I proved that M runs from minus J to plus J, right? And the J takes values, half integer values. You've seen that proof sometime. It's in an early chapter of this field theory book. So go review that. That'll help, because that's the kind of thing we're doing again, only now we've got more raising and lowering operators, and we've got two, let's see, these two are not Casimirs, right? There are two Casimir operators for SU3. So we could label our states by 4 things, not just 2. And the 2 that change when you work with these guys are the eigenvalues of H1 and H2. And they're gonna sweep out a plane. When we work just with this, we can plot, suppose J is minus 3 halves, and we act with J plus, and it's going to take us to minus a half, minus a half, plus a half, and plus 3 halves, and then we get 0. So we can plot the J equals 3 half states on a line, or the J equals 17 half states on a line. And that's because the raising and lowering operators can only change M. Let's see. So if you want to combine different angular momentum states, let's work with J1M. suppose you had a product of two J states, and I'll call this M prime. And you would like to know what the eigenstates of J squared and JZ are for this kind of product. So this could be an electron, and this could be the electron's orbital angular momentum. So this would be like L and M sub L, and J here would be a half, and this M sub S would be plus or minus a half. And you want to know, okay, in my atom, I have an electron in this state, what's the total Z component of angular momentum I expect to see? And what you do is, a couple things can happen, because the total angular momentum, you can imagine L and the half, well, they can line up so they can give you L plus a half, or they can anti-align and give you L minus a half, or depending on, that's all you get for this case, but you could have various things in between if you're adding to different angular momenta. So how do you find the resulting JM states for that? And what you do is you start with the biggest one here. And make some space here. You start with the highest one. So, let's take the angular momentum to be 2, let's say. So we've got the second orbital or orbital angular momentum, and we've got an electron with spin a half, and we want to know what the total angular momentum and Z component we should expect to see will be. So if you put these together, you're going to have a 5/2 state if these align. And 5/2, the highest state is 5/2 and plus 5/2. But now to find the next state, you act on that with the lowering operator, 5/2, 3/2, but there's a coefficient. Let's see, how do you do this? Okay. This has to be equal to the 2/2 state with the 1/2, 1/2 state. And then you apply the lowering operator to both sides of this equation. Have you guys seen this? Is this familiar? You haven't seen it,
Right.
no?
So you can start at the highest. You can apply a lowering operator,
Yeah.
which can always be built from Casimir operators. Right.
The lowering operator is built from the other J's, J1 and J2.
Okay.
J1 plus or minus I, J2. They're like the E's I had up here before. Okay.
Okay.
So, all right. So we need to do a little bit of detail here, right? I want to apply J minus to this. Well, J minus on this is just J minus for a 5/2 state. And that's the formula I wrote before. This is going to be J plus 1, 5/2, 5/2 plus 1. This comes out of that chapter 2 stuff. We've got just the action of J plus and J minus M minus 1, 5/2 times 3/2 times 5/2, 3/2. And well, what is that? That's 7/2, 35 force over 4, and minus 15 over 4 is 20 over 4, and we want the square root of all that. So that's the square root of 5. So over here we get the square root of 5, and that number, unfortunately, is called a Clebsch-Gordon coefficient, right? Okay, we got a name for the thing. That's a Clebsch-Gordon coefficient right there. There are tables of these things because people who do with atomic spectrum just use it. Okay, on the other side, we have, this is a direct product state. We have a direct product of, basically it's a sum of direct products here, 1 plus j minus, where this one acts on the second one, this one acts on the first. And we want this to act on 2, 2 cross 1/2, 1/2. Okay, so this one only sees that, this one only sees that. So we get a sum of a couple things here. When this j minus hits that, we're going to get the square root of 2 times 3 minus 2 times 1. There's an h bar in all of this, but h bar is 1. And we lower this to a 2, 1 cross 1/2, 1/2. But now there's another term where this one hits the second one, and that's going to give 1/2 times 3/2 minus 1/2 times minus 1/2, and a 1/2 minus 1/2 state. And that's 6 minus 2 is 4, so we just get 2 here times a 2, 1 cross 1/2, 1/2, plus this is 3/4 plus 1/4, that's just 1, so 1/2 minus 1/2. Whoops, oh, sorry, still the product here. There's the 2, 2 here. So 2, 2 times 1/2 minus 1/2. And notice that the m's always add up here. Here's a 1 plus 1/2, that's a 3/2. 2 minus 1/2 is a 3/2 as well. So we always preserve that z component overall. So you go through all of this, right? It's a straightforward process, but it takes a while. But okay, so what do? We start with the highest state. We act on both sides with lowering operators. And now we have an equality, square root of 5 times 5/2, 3/2 is equal to all of that stuff. You divide through the 5/2, and you've expressed this as a linear combination of a spin up electron in the m = 1 orbital and a spin down electron in the m = 2 orbital. So you know how the different possible products of these guys actually turns into a total angular momentum state. And you keep applying these operators, and you're going to get a 5/2, 1/2 at the next stage, and a 5/2 minus 1/2 at the next. Let's see, how many more? 5/2, 3/2, minus 3/2, and 5/2 minus 5/2. So you go through this same process, and you get 6 different irreducible states for the angular momentum. So what you expect to see when you look at this this electron in whatever atom it's in, all right, is that if you do the Zeeman effect, your initial line is going to split into 6 parts. All right, so you're going to see a total spin 5/2 state splitting into these 6 parts. Now that doesn't exhaust them all, because remember we have a 2m state with a 1/2 m state. There are 2 of these, and there are 2j plus 1 is, what's 2j plus 1 for 5? There are 5 of these. Is that right? Yeah, minus 2 up to plus 2 is 5 states. So there are 10 states altogether. So we don't have them all yet. So this gave us 6 of them. Now, that highest state was unique, but this next state down, I could write a linear combination of this and that is orthogonal to this one. there's exactly one state orthogonal to that. And let's see, it's going to have a minus sign here, and yeah, if you put the 2 here and a minus sign, you'll get an orthogonal state. Not hard to see what that needs to be. But that other state is going to be part of a j equals 3/2 multiplet. Its highest state is going to be the 3/2, not the 5/2. And now you can do the same thing with this one. And right, you have 3/2, 3/2, 1/2, minus 1/2, minus 3/2. That's 4 more states. You've got them all. I think you've got them all here. Let's see. If I did my counting right, that's all the states. But you keep stepping down and finding orthogonal states until you have accounted for all the states that you started with. So you've re-expressed a product of different angular momentum states in terms of the irreducible states, the single, a 5/2 m and a 3/2 m. Oh boy, yeah, okay. Thought you guys might have seen this already. Guess not, not your fault, right? Let's see, where is this? You can read it in Sakurai. I can dig up some of my notes where I worked through this. Yeah, I'll find some Klebs-Gordon notes for you guys. Where I do examples of this, probably give some simple exercises. My quantum notes, I'm sure many times I go through this. So we'll get you up to speed on that. But let's go back to particle physics, right? What are we doing here? We've got, we want to combine, we want to describe the proton in terms of quarks, right? The proton, the neutron, and other particles. We want to predict what other particles we're going to see. So how do we do it? Well, baryons are made of 3 quarks. And we choose the highest combination of 3 quarks, right? So, you've got like you've got 3 quarks totally symmetrized. And now you start acting with operators that change U quarks to D quarks or U and D quarks to S quarks. And you can find all of the states that can be built out of 3 U, D, and S quarks. Now, we use the Young tableau to figure out what symmetries we should start with. So what we're going to get with the quarks, okay, 3 quarks. Now, here's an example of Young tableau. Let's do this. So if we've got 3 quarks, but do you have questions on this? Is it roughly clear what we're doing there? I'll get you notes on it. But what we've got are 3 quarks. So you probably did fine with the Young tableau problems. Those are not hard. Hey, Kevin, did you get a chance to try those yet? Yeah, they're good, right? Yeah, and Guillermo got them, I know. Okay, so you do a couple of these first. So if I take it 3 by 3, these are fun and easy things, right? So there should be 9 states I can build out of 2 quarks, and I can put those side by side, 3, 4, or I can put them vertically, 3, 2, and I count here. There's a 1 and a 2, so 3 times 4 over 1 times 2 is 6, and then 3 times 2 is still 6 over 2 times 1 is 3. So this says that 3 by 3 is a 6 plus a 3. This is just like the Klebs-Gordon thing we were doing here, right? You would, this would contain the highest state, the the totally symmetric state where they add completely, say 2 up quarks, and then you change U to D and U and D to S, and you find, oh, we've built 6 different quark pairs. And then this one, you're anti-symmetrizing the pair. And how many ways are there to anti-symmetrize, right? 3 things. Well, you choose any one of the 3, and that pretty much determines how to anti-symmetrize. So you only get 3 of those. Now we take the next product. So we've got here, this is just counting. The Untitled is just counting. So we're going to take another 3 times these guys. So we have the symmetric combination 3, 4, and we have the anti-symmetric combination 3, 2. And so we can add this to the end, so we get 3, 4, 5. Or we can add it below the 3 and get a 3, a 4, and a 2. And then the second one, we can add this to the right of the 3, and we get another 3 times 4 times 2. And then we add it below, and we get a 3, a 2, and a 1. And now we do the counting. So this is 3 times 4 times 5 is 60, divided by 1 times 2 times 3 is 6. So we get 10. Here, 3 times 4 times 2 over 1 times 3 times 1. The 3 cancels, and we get 8. This is the same. That's also going to be an 8. And this one, we have 3 times 2 times 1 over 3 times 2 times 1 is 1. So we have a singlet. So we have a decaplet, 2 octets, and a singlet. That octet, one of those octets is the 8-fold away. Those are 8 fundamental baryons that you can build from UD and S quarks. The decaplet gives you 10 more baryons you can build from the up, down, and strange quarks, right? So this is a handy counting routine. This technique actually lets us step through, right? This is the analytic thing that you would do if you want to, well, you can bypass it actually, but we do a graphical thing. So just as what's happening here is we're starting with a highest state, and we're going to step down, step down, step down, step down. Okay, so each time we use J minus, we're moving to the left along a line of possible ends. Now, what's going to happen here is we have 2 eigenvalues for the states. So this diagram is going to take place in a plane. And what happens is we have a state, let's see, what we do, we start with the highest state. So this will be part of the decaplet, say a UUU quark. And we're going to apply one of those 3 E operators, one of the 3 lowering operators. And E12, in fact, will take us this way, a step at a time, to UUD, and then UDD, and then one more step takes us to a DDD combination. We've just predicted 4 particles. Now, if we act with E23, let's see, which will it be? It's one of the other 2, I forget. We can get a new particle here. It's going to have an S quark. It's going to have some combination of SUU. Now, when we do this detailed kind of analysis, we know just what combination of S and U quarks it is. Well, it's symmetric. So this actual state here, if we did the lowering, would be SUU plus USU plus UUS, a symmetric combination of those three quarks, two U's and one S. So by actually applying those, we can, or just knowing what symmetry we're dealing with from the Young tableau, we can figure out the form of the wave function for these particles. These are called, oh gosh, what are these called? I don't, let's see, where do I have the names of these guys? Ah, okay. So yeah, these are deltas. What's the charge of a UUU combination of quarks? What's the charge of the U quark?
1/3. Plus 2/3.
The D and S are minus 1/3. The U is plus 2/3. So three of them give a charge. It's called the delta particle and has two fundamental charges on it. This is going to be 2/3 plus 2/3 minus 1/3 is plus 1. We're actually stepping down 1 unit of charge each time here until we get down to the DDD. Minus 1/3, minus 1/3, minus 1/3 is negatively charged, like the electron. So we can easily figure out various properties of these. Now, here we're just looking at the quark content. When you do a more detailed analysis of everything, you want to know what angular momentum state those three quarks are in. So you fold that into all of this and you get slightly different multiplets, and they've got big numbers in them, and we're not going to do that. But to see what basic kinds of particle to expect, we can do this. So these next ones down, for historical reasons mostly, are called sigma stars. And this has plus 4/3 minus 1/3 is plus 1 charge. And then you can step down and step down. So let's see what you get here. Let's see that you can get an SDU or an SUD combination. And another step, you're going to get SDD over here. And you'll have a sigma star minus and a sigma star neutral. Now you step this way again, and you get a doublet. If you step this way from that one, you just are in a different part of the doublet. This is called a Xi particle. And I think it's, well, what is it? We're changing a U to an S, so it's an SSU combination. And that's minus 1/3, minus 1/3, plus 1/3. So this one's neutral. This is the neutral Xi particle. This one's going to be negative. We're changing the U to a D, so it's an SSD. And we come down one more, and we get something that's triply S. This is, I believe, a capital omega, and it's got a charge of -1. Yeah. Oh, sorry, it's an omega star. Okay, and this is the decuplet, right? This is a multiplet with 10 different particles in it. These are some of the lightest baryons. So at well, probably Fermilab in the 60s, people were starting to see these particles. And a triumph of the eightfold way. Okay, the octet is the one that contains the proton and neutron. Seeing this particle, this omega star minus in a particle accelerator, was a triumph for this model and ultimately the quark model of the fundamental particles. I don't know. Did David peek over all this in intro modern? I don't know what, every time I grab this screen, I tend to press the off button. If I suddenly vanish, we may all have to log in again. How are you doing with this? there's a bunch of new stuff going on here, but what we're doing is making predictions about what particles to expect within the quark model. And it's right. Okay, that's why 50 years later I'm teaching it. 70 years later I'm teaching you this stuff, right? Because you know, this is how we know that the world is really made up of colored quarks and leptons and all that. You make predictions. So it turns out that the quark model is hugely predictive. You know, we have these multiplets. Now, the raising and lowering operators that step us from one of these particles to another, and you can move, you know, one of those E's, one of those raising and lowering combinations will take you this direction always. One takes you that direction, the minus ones take you that direction, and the E12 goes this way, E13 and E23 go that way or that way. So you can step yourself around these diagrams using any of those and you know, get to the next particle. If you know the symmetry, right? I said that this state is SUU, USU, UUS. Well, all of these states are totally symmetric. In the octet, you have a certain, one pair is anti-symmetrized. So when you do the stepping up and down, you preserve those symmetries, and you can actually predict these combinations for each of these 10 and each of the 8 particles in the 8. Now I've just posted notes on all this, and I think reading those notes is going to be really helpful. But yeah, before that, I think the Clebsch-Gordon series is a good thing to either learn or review, depending whether you have seen it or not. Yeah, I guess I don't know if what is our undergraduate quantum. Maybe that doesn't get into the Clebsch-Gordon coefficients. We don't allocate enough time to quantum. It should be 2 semesters. The graduate quantum course should be more. You can read about this in Sakurai. Sakurai goes through this too, and I'll get you notes. So we'll get you there. So let's see, where do we go from here? Let me check my notes and see what we should be talking about. So yeah, the first thing to do actually are the mesons. They're simpler than the baryons. Now, how much do you guys know about particle physics? Let me back up on that one too. Just quick review. There are hadrons and leptons. Hadrons are heavy particles. They're particles containing quarks. So the hadrons come in 2 kinds, called the baryons and the mesons. Mesons are quark-antiquark pairs, and baryons are combinations of 3 quarks. So that's what we worked out up here. They really only come in those combinations until, within the last year or so, there's some evidence of pentaquarks at CERN. But the underlying reason for that is color symmetry. Okay, the most frequently occurring combinations, all right, low energy is up to a TeV, right? So up to pretty high energy, are all color singlets. So you assign 3 colors, red, green, blue, let's say. And to form a color singlet, there are 2 easy ways. You have a color and an anti-color. So a red anti-red combination will have no net color. or if you have a red and a green and a blue quark in a triple, that can have no net color. And still, every particle we've ever seen has no net color. The reason for it is because to see color separately, to see an individual red quark, you would have to free a red quark, and the strong force is so strong that before you can free it up, there's so much ambient energy, you create a meson, quark-antiquark pair, instead of freeing up the quark. So we don't see free quarks, and so we don't see free color. All the particles we see have zero net color. And that tells us why the only combinations we have ever seen are quark, mesons, quark with an antiquark, or quark triples, or 4 quarks and 1 antiquark can do it too. If you have a red, green, blue, and then a green anti-green, say, as a pentaquark. So we're starting to see those sorts of things too. It's basically some quasi-bound state of a meson and a baryon. Okay, so that's why there are 2 types of hadron. The baryons, 3 quarks, are heavy. The mesons, medium mass, but in high energy states, they can be heavy too. Quark and antiquark. The other class of fundamental particles are the leptons. Leptons are light particles like the electron, and there are 3 pairs of these. Each, there are 3 things that are very much like an electron: the electron, the muon, and the tau particle. I don't know why I'm not writing all this on the board. I'll write this all on the board. Have you guys seen this breakdown? Yeah. Okay. So it's already in your head somewhere. If you want, I'll write it down. But I think this is a fairly familiar chart. So you have with each lepton, massive lepton, you've got a neutrino. So the electron neutrino, the muon neutrino, and the tau particle, the tau neutrino. And then the quarks come in pairs too. You have the up and down quark, you have the charm and strange quark, and you have the top and bottom quark. Those doublets have to do with a weak interaction, which we'll talk about later. But the strong interaction only involves the hadrons, the particles built from up and down, charm, strange, top and bottom quarks. Okay, let's see. Help me out here. Ask some questions. How much of this is clear? Where does it start to get fuzzy? Okay.
Fine.
Nothing jumping out. Let's see. We can, we've described the raising and lowering operators for SU3. We have described these constants here are called the weights. And when you look at a pair of weights you get from the 2 diagonal elements, they form a little 2-dimensional vector called a root vector. This is all new nomenclature, right? That's confusing. But read Lichtenberg. Lichtenberg goes through all of this very nicely.
It rings a little bell from the end of Fell's Lie algebra class.
Sorry, I didn't quite understand. Say it again, please.
Said it rings a little bell for us. We all took Dr. Fell's Lie algebra class, and I think that's kind of the last topic we finished with.
Yeah. I talked about roots and weights in the standard form. The newer posting of the notes, let's see, or last but one maybe. I upgraded that discussion a little bit. So, make sure you're looking at the most recent version to review that. But yeah, so basically, as you vary I, you get a little two-dimensional vector. Well, those are displacements in these kinds of diagrams, right? It's just how much weight is associated with the raising and lowering operators. How much does the eigenvalue of H1 and H2 change when you act with this? You should recognize this kind of commutator, right? It's what J plus and J minus do with JZ, right? So when we argue that J plus and J minus change M, let me do it. So this is how you see what those E's do. If we've got J plus or minus, and remember we've got JZ, let's call it, acting on a JM state, pulls out M times H bar if we're keeping track of units, but let's not worry about the H bars for that. J plus or minus acting on a JM state. We'd like to know what that does. So what we do is we start with an eigenstate of JZ. And now let's act with JZ on this state, say J plus acting on JM, to see what M value we get for this thing. It turns out this is still an eigenstate, right? So the way we do this is we write the commutator JZ with J plus J plus times JZ in the opposite order, as we can do that. And we let all of that act on JM. Well, now we know how to let JZ act on JM. That just pulls out M. We know what this commutator is. This commutator, JZ with J plus, well, that's really H bar over 2, but I said we'd skip it. Let's just call it a half sigma Z with a half sigma 1 plus I sigma 2. I'm not sure if my halves are right here, but well, let's suppose, okay. Sigma Z with sigma 1 is 2I sigma 2. Then plus I times sigma Z with sigma 2 is minus 2I sigma 1. So the I is going to go away here. We're going to get a 2, so we get back to a half times sigma 1. Let's see, and we've right, we didn't do anything with that, so we still have plus a half I sigma 2. So it comes back to itself, right? JZ with J plus is another J plus. It's some constant. All right, the way I did it, a constant is a half. Let's see, the constant should probably be 1, so I probably should have used the square root of 2, but you work that all out with the normalization of states and things. But here's the basic idea. This is some number, let's call it 1, times a J plus again. So this commutator just gives us J plus. Yeah, let's multiply by, well, forget the half. Then plus J plus, this JZ acting on this state just gives M. And then we still have this state. So what this is M plus 1 times J plus JM. That's an eigenstate. That's still an eigenstate of JZ. So same thing happens with J minus, that you will get a minus sign here. So it lowers M. This raises M. Look, JZ acting on this state is M plus 1 times that state again. That means, okay, that's an eigenstate of JZ. That means that has to be proportional to j, and m plus 1. The same j, but m has been raised by 1. And j minus, if you work it through, it'll be m minus 1 here. So the raising and lowering operators allow us to step through the different values of m that are allowed. And so we just keep applying it, and we can smooth them all out. We can find them all. But the key here was that this commutator comes back to j plus. You know, there could be some constant here. It depends on, that's what the weight is. But a commutator of this form gives you a way to generate different eigenvalues of that operator. That's the generalization we're after here. And if we find operators like the ones we have do this, if we find operators that have this form with both of our diagonal operators, now we can move around the eigenvalue plane and find all the particles, that have a given set of Casimirs actually. But we find all of these multiplets, the octet, the decaplet. There's a singlet that doesn't really occur because of symmetry. But anyway, we can find all the particles by acting with operators with this type or that type of jz with j plus is proportional to j plus. When you see that, you've got a raising or lowering operator. Okay, wow. Mesons. Now, there's one tricky bit with mesons. We need to understand how to represent an antiparticle. And in a Young tableau, if we want to work out all the mesons, yeah, there's a mnemonic that, I don't know, I've never found it all that compelling, but you can write a singlet state. You guys get any questions? Any of that? Okay. A totally anti-symmetric state of 3. Right. So 3 times 2 times 1 is 3. So 3 times 2 times 1 over 3. That's 1. That's a singlet state. There's only one of them. We can think of that vaguely as the vacuum state. There's only one vacuum. There's only one totally anti-symmetric state. So we can ask what annihilates a particle? Well, a block of 2 anti-symmetrized. Right? If we multiply a 2 by a 1, right? One of the things we're going to get is that singlet. And so this anti-symmetrized doublet is the way we represent an antiparticle. Now, there's a deeper reason for this in group theory, and I'm not going to go there. I don't actually quite know what it is. What is it? It's a different representation of the group, is what it is, and we don't really need it as long as we accept that anti-symmetric pair. So if we have a quark, we're going to write that as a box. If we have an anti-quark, we're going to write that as an anti-symmetrized pair of boxes. And this works. So let's just do it. So a meson, a QQ bar pair, means we're going to take a 3 and a 3 times 2. Well, what is a 3 times 2? We get a 1 here and we get 2 there. So 3 times 2 over 2 times 1 is a triplet. So this is a triplet and that's a triplet. So we're still multiplying 2 triplets here. It's just, this gives us the contribution of the antiparticle. So we work this out. So this is our quark, this is our anti-quark. And so we can get the anti-symmetric pair and the third one symmetrized, or we can get the triple anti-symmetrization. We know that that is a singlet, and this 3 times 4 over 2 divided by 1 by 2 by 1 is 8. So 3 times 3 equals 8 plus 1. That works, except that we write this as a 3 bar if we're using the antiparticle representation, and that gives an 8 plus a 1. So what we expect for mesons, there's some singlet meson, and then there's an octet of mesons. So let's find out what the mesons look like. Now, back up. What mesons do you know? Can anybody name a meson? Sounds off, Eli.
There's the pi meson.
There you go. All right. The lightest
The
meson.
easiest one.
The lightest mesons are the pi naught and the pi plus or minus.
Yeah.
Right. So we expect those to be in this lowest lying octet. Know any more? Can anybody name another meson? You need a strange meson. Let's do the pi first. Let's find the pi, because the pion, being the lightest, actually, there's a little bit of sense happening here. There, SU3 has an SU2 subset, so we can work with the SU2 subset, and the raising and lowering operator there are the E12, and we'll see that these can take an up quark to a down quark, or a down quark to an up quark. Let's say E12 minus will take an up quark to a down quark. It can also take an anti-down to an anti-up. It can go either way. So what we're going to do is we're going to start with, let's start with a maximal state, a UU bar. And let's see, let's see, that's, that's not the one we want to start with. What we want to start with is, let's start with a DU bar. That's the lowest charge, right? Because this is minus 2/3 and this is minus 1/3. So this is probably our pi minus. And if we act with E12 plus, that's going to take a D to a U. That's our E plus. So the D is going to go to a U bar, but this can also take a U bar to a D bar. So it's also possible to get a DD bar here. And let's just be cautious about it because we haven't generated what the coefficients are, but we're going to get a linear combination of UU bar and DD bar here. Then we can apply E12 plus again, and it can do, it can do, well, a couple things. It can take this D to a U, so we could get a U D bar here. Or over here, it could take U bar to D, and we get another U D bar. Well, that's already normalized. This is going to need like a √2 or something to normalize it. But these are our 3 pions. These are neutral, right? Plus 2/3 minus 2/3 are plus 1/3 or minus 1/3 plus 1/3. So this is a neutral pi, and this is a pi plus. So we make those identifications with mesons that we know. And now we can take another step, because there's one more particle here. If we take B U bar minus alpha D bar, suitably normalized, that's orthogonal to this state. So this is some other particle. It's called an eta, and it has a mass of 548 MeV. It's pretty much the next lightest meson. So just in the UD doublet under SU2, where there's only one of these guys, we step out the pions and predict a new particle, the eta meson, that has about half the mass of a proton, turns out. So we see it. That's good. So what do we do next? Well, we want to get the whole octet, and this triplet. All right. So what have we got? We've got a D U bar here. We've got UU bar plus DD bar, or we've got U bar minus DD bar. And then we come over here and we've got a U D bar, and we identify this as pi plus, this is pi minus. One of these is, actually, I think it's the one with the minus sign. You'd have to check symmetries in detail and the other one here is the eta. So we put a circle around it to denote that there are two particles here. Now we're going to act with one of the other two raising and lowering operators of SU3. If we act with, okay, let me just figure out what these do. E plus 1, 3 or 2, 3. Let me just remind myself what those do. Now, you can check this with the group properties and, just the same way we did with J plus and J minus. But let's see. Okay, E12. Yeah, E13 plus takes this takes an S to a U, or can take a U bar to an S bar, and this is going to take an S to a D, or a D bar can go to an S bar. Yeah, that's right. And then the minus ones do the opposite. So we have E13 minus can take a U to an S, or an S bar to a U bar, and E23 minus can take a D to an S, or an S bar to a D bar. So with a little bit of work, raising and lowering kinds of stuff, commutators in the Lie algebra, we can show that those different E operators will make these changes in the quarks. And so from this table, I can act, right? I can act with anything that'll act on either a U bar or a D. Well, E23, this one takes a D to an S. So I think, let's draw that down here. That's going to be an S U bar. That's minus 2/3 minus 1. This is going to be a negatively charged something. If I act on this D on the U bar, I can take it to an S bar. So I can come up this way and find a new state that is a D and an S bar. That's minus 1/3 and plus 1/3. So this is a neutral particle. Now, what particle are we talking about here?
This is going to get us the K mesons, right?
That's right. Yes, these are the kaons. So this is a neutral kaon, and this is a K minus. And now we can step in various ways here. We could go, with the inverse of that operator up to here and get that a different way. we can go up this way, or we can use E12 to take us that way. We can move any way, and I want you to do some exercises where you check that you get the same thing going different ways. But okay, if I go horizontally, that changes a D to a U, and I get a US bar, which is positively charged. And this brings us back, but we can go any of these directions. And let's see, so what can we do if we use E12? E12 takes a E12 plus takes a D to a U or a D bar. Now, I think we need E2 minus. Anyway, we're going to change that U bar to a D bar with one of those operators. And this will again be neutral. This is minus a third, this is plus a third. So this is another neutral K. It's the K naught bar. It's the antiparticle of the K naught. Yeah, the kaons are weird in a whole lot of ways. There's a K long and a K short. They're two different decay modes. So if you produce a bunch of Ks via the strong interaction and they decay via the weak interaction, there are two different ways they can decay, the K long and K short. They also violate everything in sight. They violate charge conjugation, they violate parity, and therefore probably violate time reversal because of the CPT theorem, which we've talked about. That's pretty wild. So if you look at a decay of kaons and then consider the time reverse process, the probabilities aren't all the same. A process like that is thought, hypothesized, to have taken place in the early universe, where you don't have to conserve baryon number, and so you can have this annihilation between huge numbers of particles and antiparticles and end up with just some particles left, which is a plausible explanation for why we don't see more antiparticles orbiting the sun. It's all normal particles in our part of the universe. It's kind of an open problem, I would say, exactly why that happens. But we do see very likely time reversal invariance. We can't run the experiment backwards exactly, but the CPT theorem is basic enough that those three discrete symmetries taken together should leave everything invariant. And since kaon decay violates charge conjugation and parity, we expect it must also violate T. So the product CP is violated by kaon decays. So anyway, there is an octet of mesons, and probably half of what came to be called the eightfold way in the good old mystic 60s. There were a lot of fancy names for things. Charm, the top and bottom quark used to be truth and beauty. I took a sobriety pill and just called them top and bottom after a little while. But yeah, quarks, the term quarks comes from Finnegan's Wake. There's a line in there, 3 quarks for muster mark. And no one knows what it means, but now it means these guys, quarks. Murray Gell-Mann was a very literate guy. He was the one who came up with that name. So there's the octet. Let's see, and we can step through the baryon octet too, and there are a few things I can tell you about all of that that will be meaningful, despite needing to go back and review some things or pick up some things that were missed along the way. Before I launch into that, I want to ask about next week, since July 4th is celebrated on the 5th next week. Next Monday is a holiday. And well, we could cancel class, I suppose, or we could hold it at a different time. I would favor moving it either to earlier in the day or maybe back to this Friday or something. If that works for you, I don't know if you're all going to be traveling for 5 days around the 4th. Oh, don't do that. It'll be hideous. But in any case, how's it look for everyone? What sort of 4th of July plans? What should we do with the class? I should say that I'm going to be driving to the East Coast. So after the this next class, I'm going to be working on an iPad, probably from Maine for the next 2 or 3 lectures before we get back here. That's worked pretty well in the past. I think we'll be able to manage with that. But how does it look for next week? What do you want to do?
I would just prefer to meet in the middle of the week instead. Meet on a Wednesday, perhaps.
Okay, so Wednesday, I will be somewhere in Iowa, I think. We're driving across the country. So a week from Wednesday, we could meet this Wednesday if you want to keep going here. Yeah, let me see. The only issue there is how many notes I pulled together. I could always go back and talk about Clebsch-Gordon coefficients, though. I've just started on chapter 14. I've written a nice introduction to the standard model, a little bit of historical material. Let's see. Yeah, it's going to be hard for me to pull together very much material by this Wednesday. Let me see. Yeah, we could probably, well, once we get to Maine, Meg's dad lives in Maine, Brunswick, Maine, and we should be there about a week from Monday. Let's see, might be able to do 2 lectures that week. So let's see, let me back up here. Are you suggesting not meeting next Monday for the holiday?
Yeah, I will be moving. I'll be traveling around. I won't be going far. So timing is really just the thing, because I can kind of meet from anywhere as well. But
Okay.
I mean, Tuesday is ideal. I mean, it would be nice if I didn't have to try to work this into things on Monday.
Right.
It would be
Yeah,
doable,
I get
but-
that. Now, how about you two, Eli, Guillermo? What does it look like for you two?
I can pretty much make any time work. The only travel I have is between where I am now in Orem and Logan, and that's a 2-hour drive, so it's not a
Okay.
big deal.
Guillermo, preferences?
No preference. I'm open.
No preference? Okay. Yeah, I guess, I would like to be on the road next Monday. So, that can be after class. So we could meet Monday morning if that works. It's going to be tricky for me to have the next lecture ready much before that. I might be able to have it ready by Friday or Saturday. But I've only just started writing on the standard model. Unless you really want to go back and hammer Clebsch-Gordon coefficients. Let's see, we could do some of that. Yeah, could do a bit of that today, actually, and save the baryons for next time. So Kevin, is there a time later this week that would work for you? Or is that...
I think the earliest I'd want to meet again this week would be Thursday. But honestly, I'm a little bit flexible on that.
Yeah. Okay. So would Friday work?
Friday works fine for me.
How about you two, Eli, Guillermo? Would
I should be. I have stuff later in the day on Friday, but I should be fine.
So earlier on Friday?
Earlier on Friday works for me. What time? It's not too early, but
Yeah.
I might say like 11 or noon.
11 or noon is going to run till, if we do a couple hours, it's going to run till 1 or 2. Is that too late, Eli?
No, that'd be perfectly fine.
All right. Let's say 11 o'clock Friday then. All right. I'll send around an email and a text to Eli.
It's just so much easier.
Yeah. Oh, I get it. I just, yeah. If you all send me a text, I know how to reply. I'm not up to speed on texts entirely yet, but I do like them. They're nicely immediate.
Yep.
Okay. So let's meet 11 o'clock
11 o'clock.
this Friday, and then a week from Monday. Good. All right. Now, in the time that's left, yeah, why don't I talk about the Clebsch-Gordon stuff in a little more detail? Would that be useful to you, or would you rather just read about it? Did I do enough already? We can go on and do the baryons if your choice. Baryons or Clebsch-Gordon?
I'd say Clebsch.
Clebsch-Gordon? Okay. All right. So, yeah, we'll save the baryons for Friday. That's the real eightfold way. Protons. But okay, so Clebsch-Gordon coefficients. Okay, so first we have the Lie algebra of SU2 rotations. So now we're back to talking about spin and all that, because it's just the simplest example. And we know that we have JX, JY, JZ operators satisfying JI, JJ is epsilon I, JK, JK. Well, there are I's and H bars here, and it depends how you normalize these guys. I'm pretty sure there's an H bar over 2 here. And if these are Hermitian, we would need an I. But again, it depends on how you define the generators, but you want these to actually be angular momentum. Now, from this, we show that J commutes with everything. It's a Casimir. It's not hard to see that it commutes. Let's just do it. So if I write this as JJ, and I use this identity, pulling it out first to the left and then to the right, the other one to the right. Then this is over to epsilon J I K, this J with a JK from the commutator. And this one, we get I over 2 epsilon J I K J K J J. And J, did I do that right? Yeah, I guess I did that right. Okay, then here, epsilon j I k. Now this is an anti-commutator of j's, which is proportional to delta jk, some constant here. But this is symmetric, and this jk is anti-symmetric, so this is identically 0. We're just summing this anti-symmetric thing, so that's going to be 0. So j squared commutes with all the j's. Also, we know that we can choose j3 or jz to be probably h bar over 2 sigma z, sigma 3. That's diagonal. So we have two diagonal operators. This is basically proportional to the identity in this representation, and this is 1 minus 1. So we have two diagonal operators, and so we label states by eigenvalues of the two diagonal operators. So here we get j plus 1 h bar squared times j m, and jz acting on this j m is m h bar j m. And you can read in chapter 2 where I worked through all states of all rotation states, all irreducible representations of rotations is what the section is called. But we show that m ranges from minus j plus 1 up to all the way up to plus j, and that's 2j plus 1 different values. J is any half integer, and 0, 1, 2, 3, and so on. Right. So that describes all of the states. Any question on that? Okay. So now.
It's fermions and otherwise.
Sorry, what?
That's the fermions and otherwise. So we're going half and whole integer.
Yeah, the half integer correspond to fermionic, to spin states. Yeah, that's right. So spin 1/2 would be n equal 1.
Yeah, I just things got more general than I thought they were when n is 0, 1, 2, or 3 rather than just 1 or 3. Because if n is 0 or 2, those are now bosons, right?
Yeah, that's right. So any even integer is going to give a bosonic state.
Yeah, and that's no issue. This discussion is general enough for both.
Yeah, that's right. That's right. Yeah. So 2j plus 1 is going to be n plus 1, and so n equals 0, 1, 2, 3 means we have we have a representation of the group in every dimension, right? So n plus 1 is 1, 2, 3, 4. So there's a one-dimensional vector space, which is a scalar. There's a two-dimensional vector space which is spin up, spin down. A three-dimensional is an ordinary 3-vector, and a four-dimensional is a spin 3/2. We don't. There are some spin 3/2 particles, but we can get spin 3/2. Say if we have 1 unit of orbital angular momentum, which is L equals 1 or J equals 1, and the electron spin. If those add up, you'll have a hydrogen atom with a spin 3/2 total angular momentum for the electron. And that's the question we want to address right now. How do we figure out what states we are going to see? Now, what we do is we replace JX and JY by, let's see, don't need that. But we let J plus and minus be JX plus or minus IJY. And if we just work one of these out, if I have JZ with JX plus or minus IJY, well, we did this earlier, right? And this turns out to be plus or minus JX plus or minus IJY. So it comes back to itself with a plus or minus sign. And now, let's see, and those, of course, those can't change J because all three of these commute with J squared. So J squared doesn't get changed by this. Then we know what J plus and J minus do on a JM state, because it cannot change J, but J3, JZ, let's say, does change, and we just work that out. That's the commutator of these two, which is just plus or minus J plus or minus, plus these two acting in the opposite order will just give us an M times J plus or minus, and times Jm again, which is M plus or minus 1 times J plus or minus acting on the Jm state. So this combined thing is still an eigenstate of Jz, but its eigenvalue is increased or decreased by 1. So we can identify J plus or minus on Jm as some proportionality constant times J with M plus or minus 1. It's a different one in the same vector space, in the same 2J plus 1 dimensional space of states. Okay, now these coefficients, they're the things that end up giving us Clebsch-Gordon coefficients, and finding their values depends on normalizing the state. So we know that this has to be proportional to the Jm plus 1, but we want the Jm states to be normalized to 1. And so to do that, you take the conjugate. So if I have J plus on Jm, well, it's easy to see that the dagger of J plus is J minus. Right, it just changes the sign. These guys are Hermitian. So the if I take the dual of this state, it's Jm acted on by J minus, and then we have J plus acting. So if I want to find the norm of this state, right, that's right. If we use the lambda here, this is going to be lambda squared times, right? So this is, this combination is lambda times a J m plus 1 state. We assume the J m plus 1 is normalized. So we'll just get a lambda squared here. But then we can work out what this is. J plus or minus is Jx minus Ijy times Jx plus Ijy is Jx squared. Then we're going to get a Jy squared. And then we get I times the commutator of Jx with Jy which is, okay, jx plus jy I can write as a total j squared minus jz squared. And this I, okay, the commutator of these, what did I say, is there's an I, so I think we're going to get a minus sign here and a jz and an h bar. I think that's right for the commutators. Top of my head here, but we know eigenvalues of all of these, so I can rewrite the j minus j plus in terms of j squared and jz. So lambda squared has to be what we get. All right, I want to sandwich this operator between the jm states. So what I'm going to get, this is going to give me a j times j plus 1. Then we have minus, this is going to give me an m squared. This is going to give me an m. And there's an overall h bar squared. So that's j plus 1 minus m plus 1 for j plus. For j minus, you just get a minus sign here if you work that out. That's an exercise. So work out j plus times j minus, and you'll get the coefficient for the other one. So what that says, I claim, is that we found this lambda, and if I take it real, I can choose the phase, that j plus acting on a j m state is going to be the square root of all that stuff. j plus 1 minus m plus 1. And an exercise, if I put a minus here, I put a minus here, exercise. Just check that to see that you're getting it all. It's just the same thing I did here. So now times the raised state at j m plus 1. So now I know exactly how j plus and j minus act on my basis of states. So now the whole Klutch-Gordon thing. Now I can say, suppose we want to know the electron configurations for helium. There are 2 electrons. They're each spin 1/2. But so we could go in and try to measure the total angular momentum of each electron. Suppose they're both in s states, but well, they can't necessarily both be in s states. But let's see what their angular momentum is. And to find that, we have a 1/2 m for the first electron and a 1/2 m, call it m2 for the second electron. And what we want to know is how those angular momenta combine to give total eigenvalues of jz and j squared. Well, there are 2 states here, and there are 2 states here. So we expect there to be 4 states. Now, if both of the electrons are spin up, right, then their spins are aligned, and that's got to be a total, the total spin is aligned, that's going to be spin 1. And because it's not hard to show that the m's always have to add. If I act with let's see, yeah, if I act with jz, this is going to be a sum of some kind of j and m states. But if I act with jz on this, I'm going to get m1 plus m2 over here. And I'm always going to get m over here. So m1 plus m2 always has to equal the total m over here. whatever equalities we come up with, that half and that half always add up to that m. And it's an easy theorem. It's just apply JZ to the equality. So our goal then is to find out, what these sums are for each possible set of values for the m's. So to do that, right, we have one relationship here. I'm going to act with J minus, call it J1 minus cross the identity plus the identity. This is how you act on a direct product. You J minus acting on 2. So this operator is the same as just J minus acting over here. So I let this act on that set, I let J minus act on this. And we've found these coefficients, so we can carry that out precisely. All right, so if I let this act on these, I get one term where J1 acts on this first kit. And I'm going to get the square root of, all right, J is this half. That's a half times a half plus 1 is 3 halves. Then I subtract m times m minus 1 is minus a half. There are h bar squareds here. And that's going to lower this to a 1/2 minus 1/2 state. And it's going to leave the 1/2 alone. That's this first term acting on this pair. Now I let the second term act on this pair. It's going to do the same thing. It's going to give me this same coefficient, which notice happens to be 1 in this case. 3/4 plus 1/4 is 1. So I just get 1 here times. Now it's going to lower the second one, the second m. And all that has to be equal to J minus acting on this. So I'm going to get 1 times 1 plus 1 is 2 minus 1. 1 minus 1 is 0. So that goes away. So the square root of 2 times 1, 0. So my 1, 0 state is equal to 1 over the square root of 2 times the sum of these two. That coefficient is 1. So I get, let's just call this a minus state cross a plus state, because plus and minus we've used before for the Z. And then a state where this one is plus and the second one is down, spin up and spin down. So now we've got 2 results. We already know the 1, 1 is equal to a product of plus states. You okay with my condensation of the notation here? So by this, I just mean this outer product of the 1/2 plus a half with the 1/2 plus a half. So I'm writing this as just plus that way. Now I lower this again. J minus acting on 1, 0 is going to be the square root of 1 times 2 minus 0 minus 1 becomes plus 1. That's the square root of 3. Is that right? Let's see. Oh, no, sorry. 0 times minus 1. There we go. So just the square root of 2, and we get a 1 minus 1 state here. Lowers m by 1. On the other side of the equation, this has to equal, right? We're going to act with the lowering operator on this whole thing. So that 1 over root 2 is still there. And then, okay, we're going to lower this, lower that, lower this, lower that. But look what happens. If you try to lower a spin down state, you get 0. let's prove it. J minus on a 1/2 minus a half state is square root of 1/2 times 3/2 minus a half times minus 3/2 equals 0. So the coefficient itself goes to 0 automatically. So lowering a spin down state, you can't lower it any more than spin down. So when this first operator here acts on this, we get 0. When the second operator acts on that one, we get 0. Now, when J minus acts on J plus, it's the other coefficient, it's this one, which we found to be 1. So J minus acting on this combination, we have the 1/√2, and then we're going to get, here we're going to get minus minus when we lower this one. And then here, when we lower the first one, we're going to get another minus minus. And that's 2 over the square root of 2 is the square root of 2. We get a square root of 2 here. It cancels, and we see that 1 minus 1 is equal to 1/2 minus a half cross 1/2 minus a half. We could have guessed that, right? When they're both down, it's the same as both being up, really. They've got to combine. There's only one possibility. So when you do some examples of this, you will see that you always have this symmetry between, the positive values of M and the negative values of M. It's always symmetric in the coefficients and stuff. It's a quick check on whether you're doing it right. So we've generated 3 states. We find we have a 1M triplet. Okay, there's 1 state missing, right? We know we have to get 4, but we also can see that the 1, 0 state is not the only thing you can make out of minus, plus, 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 minus. There's a state orthogonal to that. And it's not difficult to write it out, to just see what it has to be. These things do have a sign convention, a phase convention, but it won't matter for us. There's a singlet state, a 0, 0, which has to be orthogonal to this state. There's only 1 state orthogonal to this, so it's uniquely determined up to phase. 1/√2. Let's take it to be a half. Let's see. Well, let's match that. Minus a half times a half. That's the plus plus state. But we'll put a minus sign here, and then a half, and times a half minus a half. So I claim that this state is orthogonal to that state. Everybody clear? Okay, good. So what we get is that the 2 electron spins give us a triplet and a singlet. So we get a triplet and a singlet. Now, that's orthohelium and perihelium, right? These are 2 states of the helium atom, where in one state it's a symmetric combination of the 2 electron spins, either both up or both down or opposite. It's a totally symmetric state. Now, these are fermions. We know that the fermion wave function, the total wave function, has to be antisymmetric. So if we have a symmetric spin state for the triplet, then the spatial wave function has to be antisymmetric. On On the other hand, the singlet state is antisymmetric, and so it's going to have a symmetric spatial wave function in order to make the total antisymmetric. Now, a symmetric wave function puts the electrons in closer proximity on average than an antisymmetric spatial wave function, which means the antisymmetric spatial wave function will have lower energy. So the lowest energy state of helium is the triplet. And you put a magnetic field on helium, you'll see the lowest energy state split into 3 lines, right? You can slightly separate the energies of these triplet states because a magnetic field couples to M, right? It couples to the Z component of spin. So a spin up in a magnetic field and a spin down in a magnetic field have different energy, slightly different, not enough to make it overlap the next energy level up. The next energy level up is a singlet state. Magnetic field on that does not split the lines. So we can see the singlet and the triplet very easily because we have characterized the states by irreducible representations of the rotation group. So there's a direct correspondence here to what we physically will measure for the Z component of angular momentum. These we can also ask about the effect of the orbital angular momentum. So an S state has L equals 0. That's L is just J when J is even. Okay, when you have a bosonic state, and the let's see, yeah. So you can take a 1m. Suppose we're dealing with the total angular momentum of the electron in excited states of hydrogen. So you've got the electron with spin up, spin down, right? In an S state, you've got 0. So you've just got those 2 states. In an L state, right? L means J equals 1. So you've got 3 states there and 2 spin states. So there are 6 states possible for L states of angular momentum. That you've probably seen the loads. There's one this way and one that way and one the other way. Maybe you've seen these probability distribution diagrams. There's nothing you can't find if you Google enough, but they're out there somewhere. Oh, you guys are suddenly looking tired. We're about done here. So try that one. Try adding together a J equals 1 with a J equals a half, or 2 J equals 1s. Try a couple of these, and I will send out some notes on this. So for low values where you're so yeah, 2 L equal 1 systems, you're going to find 9 states. The highest one is going to have J equals 2. 2 times 2 plus 1 is 5. So that only gives 5 of the states. Then there's going to be a 3, a 5, and a 3, and a 2. Let's see. I'm probably doing something wrong. 2J plus 1. J is, let's see. So let's see, 3 times 3. We need 9 states. Yeah, okay, that's it. 9 states. Yeah, so you'll have a 5 and a 3 and a 1. So what I'm saying is if I multiply 2m by 2m, no, sorry, 1. There are 3 of these and 3 of those, so a total of 9 states. These can add up and give me a 2m, and there are 5 of those, 2j plus 1 of these. So there are 5 states here. So I know that, there's also going to be a 1m. 1m, 2j plus 1 is 3. So I still haven't covered all the states. There's going to be a 0 state as well. So using the, by checking orthogonality with the first state down, you'll be able to find this state. And this state will have a middle state that can be, this has to be orthogonal to the m=0 states of both of these. So using orthogonality for all of the different states that have the same m value, you can find all 9 of these states as a quintuplet, a triplet, and a singlet. Is that enough for today? You want to, yeah, you good? All right. So yeah, let me see if I can't find you some notes on this, and I'll post them on the Canvas site, so you can read up on this. And let's see, who knows whether Tyler and Alex know anything about this stuff or not, but they'll be able to read about it there. So what did we end up saying? Friday at 11, right? Okay, good. Yeah, thanks for your patient attention. And yeah, come back with any questions on this stuff on Friday. Yeah, I threw more new stuff at you than I expected. I thought you'd probably seen the Klepsch-Gordon material, but yeah.
I forgot what it was called.
Yeah, we can fill in the gaps. It's yeah. I
I've
imagine
seen it.
you
Like
must have
those,
seen
like
it.
large tables.
Yeah, that's right. Yeah, they make
rows.
tables of these things. That's right.
Yep.
And
Yep.
I'd rather go through these steps than try to figure out how to use the tables. But the tables are, they're just these coefficients. So if someone asks you about a Klepsch-Gordon coefficient, well, it's 1/√2 here, or it's whatever coefficients arise in these things. Yeah, this is a pretty simple one, but sometimes you'll see a √3 or something like that, or 2/√3. They're just normalizations. You
Yeah,
can look,
and it was the finding the orthogonal state was the one that clicked my mind. It's like, oh yeah, I have seen this before.
yeah, yeah, yeah. It's kind of fun the first few times, so go have fun a few times, and then this is what we're doing when we construct the baryon decuplet, baryon octet, and the meson octet. We're using raising and lowering operators much like this. If we were to work out the normalizations, we could actually give the numerical combinations, but in fact, they're just simple things like 2/√3 or 1/2√3, or you can just see what it would take to normalize the states.
Oh, the direct product basis for baryons, it's 3, right? Because there's 3 quarks that we're looking at.
Yeah, that's right. That's right.
Okay.
Yeah, so try it. Try it for Friday. You can read about it. I've posted this. So yeah, this chapter, what is it, chapter 13, is basically done and posted. So come with questions on any of this material on Friday, and we'll clear it up. We'll run through the baryon, decuplet, and octet, and give names to all the particles, and that's fun. These things are really seen, and excited states of them are seen. So it turns out that yeah, what would you call it? There's okay, so there's chemistry that deals with all the electron states, right? Then there's a thing called nuclear chemistry that looks at states of nuclides. So any combination of bound states of neutrons and protons, no matter how fast it decays, there are about 3,000 of those. Then there's something that you could probably call quark chemistry. When you fold in the spins of these things in excited states, one of the last things I talk about in chapter 13 are how you name these things. They're given the same names as the ones that occur in the lowest energy decuplet and octet. Those names are given with stars, or most frequently, okay, there's a lambda baryon in the decuplet, right? Well, then excited states decay, but they have a characteristic mass and they decay very quickly. So any particle that decays very quickly is just, it's called a lambda paren, the energy of the particle, called the mass of the particle, or a xi particle paren, 1240, because it's 1240 MeV particle. So there's a little bit in here about the nomenclature too. Aside from that, go to the particle data group pages and take a look at, I have a couple of links to it in the book. Look at the summary of all the particles, all the baryons, there are, I don't know, 100 baryons we've seen or something. They're all called lambda or delta or something. But then start browsing around a little bit, just explore some, because it's, it's fascinating. But tear yourself away by 10 o'clock Friday morning, 11 o'clock Friday morning, because we'll be back here. Okay. Thanks, guys. Have a good rest of your day. See ya.